So we started on animation. We'll continue talking about animation. So what we basically started looking at was the usage of splines in the context of animation. So we are going to look at one of the applications where splines can be used for the purpose of animation. So I call that as spline driven animation. So the idea here is, the question which I am going to pose here is that, let us say you have a trajectory specified in space where the movement of the camera or the object is taking place, and it is desired that the motion along the path which is generated by this spline has got uniform speed. Okay, that's what we want to obtain. Now the issue here is that, let's say if I have a two-dimensional case where x and y are represented through this QU, so it's a parametric curve in U where U is between 0 and 1. Now if we want to generate the movement along this curve with a uniform speed, what we really want is that for a given time interval, the distance which is traversed along this curve is the same, right? If I fixed, let's say, interval t is equal to 1 or 2, whatever time, then the same amount of distance I will be traversing along the curve, right? So basically it's an equidistance traversal along the curve. Now one may start wondering is that the fact that it is a parametric curve in U, then will the uniform, or let's say equidistance interval in U would provide me an equidistance traversal along the path? The answer is yes or no? No, because it's actually a polynomial in U, right? And so if we are talking, let's say, cubic case, then it is something like a u to the power q plus b u to the u square plus c u plus d, right? So clearly that is not the case, right? It's not a linear segment where we are trying to traverse. It's actually a curvilinear path, right? So one thing which is desired from here is that I want to have equal arc lengths, right, for some spacing in U, right? And this equal spacing in U does not guarantee equal arc lengths, that we have established, right? So in some sense I am trying to reparameterize this curve in such a way that that parameter gives me the point or the location on this path at an equal interval if the parameter is with an equal interval. Okay, that is a desirable situation. Now the question is, can we do this? We can. So how can we do it? Any suggestions?
Maybe we can differentiate it with respect to time and take the final function.
Differentiate with respect to time. Okay. Well, the thing is that, see, it's a very interrelated problem. We want to traverse equal distance here, which is the arc length, right? And that is what we want to use it as a parameterization to give us the curve. So we are sort of looping around, right? It's not analytical. Okay, so I cannot solve it analytically. So now the way we want to address this problem is, let's see it. So let us try to see the measure which we are using, the arc length. How do we compute that from a given curve, right? So let's say if I assume that the curve is a cubic curve represented through this, right? A, B, C and D here would turn out to be the vector terms, right? Because this is actually, I can get the x coordinate also using this, y coordinates and z coordinate, right? So given that I have a cubic spline curve represented in this fashion, which is shown here, and let's say at a distance or an interval of du on this curve, I have a point qu and I have a corresponding point qu plus du after the interval du. Now if this interval is small enough, I compute ds, which is the arc length. So I am assuming this is equal to this, right, for a small enough interval. Then this is nothing but the distance, Euclidean distance, which would be computed between this point and this point, right, which is nothing but square root of dx square plus dy square plus dz square, right, just from here, dx dy dz, just that distance. Now the fact that I am using a parameterization in u, I can always represent this in this form. It doesn't really change anything, right? Then, so I have ds, that is the arc length for a point qu and qu plus du given by this. Fine. Okay, now I take an integration of that, which I call it as, let's say, a of u, from some starting point for the parameter u naught to u, and I integrate this, right? Okay, so this in fact gives me s. So I am basically establishing a relationship between s, which is the arc length, and the parameter u from where I compute the curve. That's what I am trying. So in other words, qu, which is the parametric curve I have with me, now becomes this, because I can get u as taking as A inverse of s. Fine. Now the fact that A is not an analytical function, so A inverse s cannot be computed analytically, right? So we are trying to find out this quantity, which is u is equal to A inverse s in some fashion, knowing that this is not analytical. Okay, so in other words, we are now reparameterizing in s with this relationship. Either you say s is equal to au, or you say u is equal to A inverse s. Right? So as far as the formulation is concerned, we are able to do a reparameterization in s of qu. The fact, now we have to figure out how do we do that computation. Right? So let's see. So what is the problem we are stating? We are stating the problem as find u is equal to A inverse s. That is the problem we are stating, given that we can actually compute s in some fashion. Fine. Now there is a property which can be of help, which is that this A, which is the relationship function between u and s, gives us a monotonically increasing values. that's a fundamental property we need to have for the parameterization, in the sense that if I have u1 less than u2, then au1 is going to be less than au2. So this monotonicity has to exist. Fine. So let's say if I have au given like this, then it has to monotonically increase from u1 to some value u3. Right. Now the statement of the problem becomes that given, let's say, the interval of u, the total interval of u, given this relationship as au, right, how do we find out u? For some value of s, let's say s alpha, right? So how do we do that? We can use this property. Okay, so we can actually do this using what is called as bisection method. Somebody suggested earlier one can do some binary search kind of a thing. So it's a bisection method which exploits this monotonicity, because let's say for some s alpha, one can start with the entire interval you have of u, in this case say u1 to u3, you obtain u2 which is in the middle, find s2 corresponding to this u2, now for the given s alpha which is known to you, you look at how this is related to s2, right, and use the monotonic property, stating that if s alpha is less than s2, would basically imply that u alpha is in the interval u1 u2. It's on one section of the interval, which is u1 u2. If s alpha is greater than s2, u alpha is in the interval u2 u3, right? And this you continue, so you keep doing this bisection depending on how you are located in each of these intervals, right? So once you have figured out that, let's say, s alpha is less than s2 and this happens to be the interval, and you are, let's say, still far from s alpha, having computed s2, so you compare s2 to s alpha. If the difference between them is large, you do again the bisectioning, keep doing that until you satisfy some threshold, right? So this is using bisection method. Now what have we done? We have basically computed u alpha, provided that we could get s alpha. Fine. That's an underlying thing, assumption. Now how can we get s alpha? So basically looking at how do we get s. Now, so this is the formula for s we have already looked at, which is an integration of this. Now qu is known to you in parameter u, and let us say we assume this to be a cubic case. Then what we are saying is that, so I can actually do a substitution of this, that means the individual terms for x and y and z from qu, which will be in terms of u, take the derivative here with respect to u, substitute here, do the squaring, take the square root, get something like this. So basically this expression can be written in terms of u. Fine. Now what we need to do is we need to get this s. Now this is sort of hard, right? Analytically you cannot find out, therefore you have to apply some numerical method. So have you studied the numerical methods for getting the integrals? Simpson's method, Newton-Raphson method, all of these, right? CS 210. So one of those, use it and get this numerically. Fine. Now all this looks good. Good means, yeah, one can do it. But there are still problems. I mean, even doing this is not so easy. So alternatively, what you can do is you can use chord length parameterization, which is straightforward. You have seen it, right? So there we are saying that this parameterization u is actually determined by the chord lengths between the data. So if I have the data at different points, so all we are doing is computing this chord length, which is the distance between the two consecutive points, and use that as parameterization. So this we have seen it earlier while we were talking about parametric curves, even for getting the interpolating splines. So chord length parameterization is in some sense approximates arc length parameterization, right? If you think that these chords are small enough and would capture the distance along the curve. Fine. So computationally it becomes handy. You don't have to do all that integration business. Okay. So now what have we basically achieved? We basically achieved that there is a way by which you can find out the position of equidistant points on the curve using reparameterization. That's what we have seen. So that gives us the possibility of obtaining uniform speed. Let's say, but what if we want non-uniform? Right. So as we had seen before, we are basically looking at, so let's say there is some sort of a notion of velocity or speed curve, which actually relates s and t. T is some parameter which is, let's say, your timeline, and s is a positional parameter. Fine. So combination of this is basically determining for you the speed. So this curve, for instance, is an indicator to a slow start and a slow end. Now in order to incorporate this, it's sort of very easy, because the first step is going to be given this t parameter, which is the indication of your frame number or the time where you want to compute the position along the curve. You get the parameter s, which is nothing but through this function which is known to you, you get this S. Use this S for getting this. Okay, so 1, 2 and 3, that's the third step. That would locate your point here. Fine. So we can incorporate this velocity curve to locate points along this curve. Okay. And this itself could be a spline curve. Right. So splines can be used not only to give you a spatial path, can also give you the speed path or speed curve. Okay, so this is, let's say, some of the applications we can think of using splines, other than just doing an interpolation of the keyframes. Like earlier we said that keyframe in-betweening can be done by interpolation, and that interpolation can be linear interpolation, or it can also be using splines. But this is in a slightly different context, because here we are specifying the trajectory or a path and we want to move along that. So this is useful if you want to, for instance, design a walkthrough of a scene. Fine. Okay, so next I'll basically give you some sort of an example of generating animation, which you must have seen. So have you seen morphing? Morphing. No. Okay, so if you have not seen, you will see. So this is actually an example where we illustrate the concept of keyframing. That's one thing. And how do we then perform the in-betweening of those keyframes? Okay. So here what we are saying is that morphing basically means some sort of a transformation of object shapes from one form to another. Okay. So you must have seen lots of commercials nowadays in television where one form changes to another form, or even the special effects in many of the films. Right? So then what we are saying is that each form from where we want to change, or which is a particular shape of the object, is considered as a keyframe. Right? Now there is an issue that if I represent one shape, one object shape using a keyframe, and then I need to perform an in-betweening between the keyframes, I must have a common topology before I can apply a linear interpolation, or an interpolation for that matter. I need to have common topology. What do I mean by that? Let's take an example here. You have a shape like this, you have a shape like this. So this is one keyframe, this is another keyframe, and what you're trying to achieve is a transformation from here to here. Fine. Now the fact that this segment has got only 2 points, and there are 2 segments here and 3 points, I cannot apply just any interpolation. How do I do it? Unless I have same number of points and same number of segments. So one has to establish some common topology between them before you can perform an interpolation. So one possibility could be that you add a point here. If you add a point here, then you are saying that there are actually two segments, 3 points, here also 2 segments, 3 points, and then you can perform interpolation to get an intermediate stage. So clearly this is a contrived, simple example. Real life situations are definitely complex and hard. Right? Imagine there is a horse and there is a cat, right? And they have different number of polygons, different number of points, and you have to morph horse to cat. It would be hard, huh? But it's possible. Okay, so what I will illustrate to you further is an example of morphing. So morphing is a generic term which is a metamorphism or transformation of one shape to another shape, which could be in 2D, which could be in 3D, right? So what I am going to illustrate to you is through image morphing. So we are restricting this to a 2-dimensional case. Okay, and this sort of does bring and illustrate it to you the concept of keyframing, because there is a notion of assigning these keyframes and then performing an in-between. Fine. So let's see. So here we are talking about image morphing. So here the problem statement is that you want to do a transformation of one image, let's call that as the source image, to another image, let's call that as the target image or the destination image. Fine. Now again, there are certain sort of requirements you need. When I am talking about a transformation which is happening between one image and another image, just the way I was talking in terms of the topology, here one needs to have the sizes of the images to be the same. So I need a sort of a normalization which will make these two images of the same size. Okay. Now another thing is that when you are doing this image morphing, so let me ask you, if you were to ask to do image morphing without knowing what it is, how would you do it? So you have understood the problem. There is a source image, there is a target image, right? And all you are trying to do is obtain the in-betweens of this source and target. Fine. How would you do it? Any idea?
Should we interpolate the two pictures pixel by pixel?
Okay. So here is a proposition. The proposition number 1 is that I have an image, I call that I1, right? And let's say we have performed the normalization. That means I have another image, call it I2, which is the target image. So this is the source and this is the target or the destination, and they are of the same size, so they are normalized. Okay, so proposition 1 says that do an interpolation of pixel colors, right? So there is a pixel here, there is a pixel here, right? You mean to say that is the same pixel, right? So x y here, you have x y here, same location, fine. So at any intermediate stage, call it I, it is some sort of an interpolation. Let's do linear interpolation of, let's say if I call this as a I1 xy, okay, plus t I2 xy. This is what you're saying? Okay. So you all agree to this? Yes or no? How many of you agree to this? One. Only one. 2, 3, 4, 5. And rest don't know or don't agree? Don't agree. Okay, so I don't agree. So can you tell me why I should not agree? So let us take a concrete example. See, I just put two images like a box, right? Now let me try my drawing skills. There is one creature here. There's another creature here, right? And basically I want to do some sort of a transition from here to here, isn't it? That's what I am calling as morphing. So now do you see a problem, what you were proposing last? There is a problem. The problem is that using this method, you are not bothered about the spatial features. All you are doing is intensity interpolation of the pixel. So you are basically doing a cross dissolving of the two images, right? Overlaying one image on the top. Right? So if there are two human beings, not necessarily fully aligned in the image, the cross dissolving is going to have at some intermediate stage 4 eyes, 2 noses, isn't it? You don't want that. Fine. So there has to be some feature correspondence. Without that, this won't work. Fine. And then what we are looking at is that once you establish these features between the source and the destination, then some spatial transformation or deformation is happening to carry the feature point from one keyframe, or let's say from source, to the destination, because this feature may be located at different point. So there is a spatial transformation or deformation which is happening for the feature, right? So then you basically do this deformation for the intermediate frames as well, okay, through interpolation for instance, and then do a color blending. Color blending is what you propose to have the blending of the two images, okay. So this is the outline of the method. That's what you need. Okay, so let me illustrate it further. So this was the source image, this was the target image. If you see it here, there are 1, 2, 3, 4 eyes, right? 2 noses, and I don't know how many lips. Okay, so this is when no feature correspondence was done. It's just a cross dissolve. All was ascertained is that the size of this image and the size of this image, they are the same, and they are, if you look at grossly, they are sort of in some sense aligned, right? It's not 90-degree rotated or anything. Even then you have problems here. So this is actually called as ghost effect. Yeah? 2 eyes turning to 4 eyes, like a ghost. Right? So now to to fix this, we need a correspondence. That means this eye needs to go to this eye, and so on. Nose has to go here. So I need to specify the correspondences between the source and the target. So this can be done manually. This can also be done in somewhat automatically. Right? So if you have done image processing, maybe you can do some automation. Otherwise, you have to specify, yes, this point goes there. Okay. So what we have done is we have chosen a certain number of features which we want that they should correspond between the source and the destination. Okay. So then there are several methods, and one of the method is using triangles for performing this, which would enable you to specify or obtain the spatial deformation which I was referring to. Right? So what we have done, we basically have marked the feature points onto the source and target image. Right? Now what we need to figure out, see, just marking these feature points doesn't really solve the problem. We need to figure out what is the transformation which has happened. As long as for these features is concerned, you can establish the spatial transformation, because you know that this point has gone there, right? So you know the offset in XY for a particular feature point. But what happens to the rest of the pixels in the image? So in some sense, you need to obtain a deformation of the entire image through these feature points. So for feature points, you are saying, yes, this point goes there. But for the rest of points, you would use that information for the feature points. Right? So we basically, what we call it as, we obtain the warping function or the warping transformation for the image. Okay. So one of the ways to do is that you have now, let's say what you have done is you have given these points as the feature points which would correspond between the source and the target. So this point goes there, let's say this point goes there, and so on. Okay. Now what you have done is you have applied a triangulation of these points in order to cover other points in the image. Okay, so in a way what we are saying is that this triangle corresponds to this triangle, right? So the transformation is from this triangle to this triangle. So for each triangle I know the transformation through the feature points, right? Then it is a question of finding out for any pixel inside this triangle what is the transformation. Is it clear? So one thing is that this triangulation which we are applying here, this has got to be the same here topologically, which is that if I join this point to make the triangle, I should have a triangle joining these 3 points here. That is what will establish the common topology of the triangulation, right? If I obtain some other triangle joining this, then I am in trouble. So I need to have the common topology between this and this. So it's the same triangulation if you want to see with respect to the vertices. It's just the location of those vertices which is changing, right? But the connectivity of the vertices is the same. If it connects to vertex 1, 2, 3 here, it also connects to vertex 1, 2, 3 here. Right? So now getting an intermediate frame here. So this is what is happening to the source, this is what is happening to the target. Now we are interested in getting some intermediate form. So intermediate form, which is basically given to you for a particular time interval. Let's say if I say this is at t is equal to 0, this is at t is equal to 1, right? So I am looking at for some t, let's say 0.5 time, what happens here. All I need to do is use this time as the interpolation parameter and perform an interpolation between this and this, the triangulations. And get this. So now I am basically able to perform the shape transformation in time between source and destination. For any frame between source and destination, I can obtain what is the spatial transformation, which is nothing but an interpolation from source to destination. The next question comes, how do you render this? You obtain these triangles. How do you render this? Because ultimately what you need is to render the image here. So how do we do that? Okay, see, as far as this point is concerned, which happens to be the feature point marked, this point. So let me use this. okay, see, we are talking about this point corresponds to this point, fine. This point corresponds to this point, and this point corresponds to this point, fine. And we obtained the intermediate frame like this. So this point is basically an interpolation from this point and this point, right? Similarly, this point is an interpolation from this point and this point. Okay, so let us say if there was only a question of rendering this point, then all I would have done, apply the same interpolation to the intensity. I know this point, where it is located, so I know the corresponding colors in the image or the pixel values in the image. Here also I know the point where it is located, and therefore I know the color values of this, the pixel values of this. So all I need to do is perform a linear interpolation between the colors here and here to get the color for this, right? So it's basically interpolation not only at the position level but also at the color level for this point, right? But what do you do a point here? So when I say for this point, therefore you can do for all the feature points the same thing, right? Just an interpolation of the color intensity. The question comes, what do you do for this? Excuse me?
Area interpolation.
Linear interpolation, yeah. You have done similar things. You have done similar things, right? So within a triangle, if you want to perform such an interpolation, what do you do? What do you use? Barycentric coordinates. So that's what we do. So basically we are looking at an interpolation in triangular domain. So given the triangle through P1, P2 and P3, you are representing a point P inside the triangle using P1, P2, P3. So, and that is through the barycentric coordinates U, V and W. And this is how we compute the barycentric coordinates using the areas. So that we have seen earlier. Fine. Okay. So how do these barycentric coordinates help? Well, we can locate a point inside triangle, but how is it helping? Any idea? Okay, so what is the question we are asking? We are asking that there is an image which is the intermediate image, fine. So I'll just draw one triangle, okay, and that can be generalized. So this triangle is obtained let's say from these two triangles. So this is my source and this is my target, right? So So all we are saying is that this particular point corresponds to this particular point corresponds to this, and so on. Okay. So these points have been located now spatially. You know where the x, y of this particular point is. We want to render this, and I have already told you the mechanism of rendering this point, which is to take the intensity interpolation at these points. Fine. Now the question which is being asked is what happens to this point. We said yes, we can perhaps use barycentric coordinates. How can we use barycentric coordinates? Okay, let me ask you this question in this manner, that this point P corresponds to some point here, some point there, right? Let's call this as P target, P source. So now the question is how this P is related to PS and PT.
Exactly the same as the vertex point.
What do you mean by that? Exactly the same as a vertex point. See, this P is inside this triangle. Okay. Let's say given the point P here, let's pose the question, can I locate PT and PS?
The same UVW.
Using barycentric coordinates. Right, so that's where we use barycentric coordinates. That now we are saying that now the question which is here is that I would render this triangle, and that is the question we are trying to solve. In other words, I am going to find out the pixel values of all the pixels within this triangle. So given this point or given this pixel inside the triangle, I can obtain the corresponding points for the target and the source, which are PS and PT, and now I can perform linear interpolation or whatever interpolation I am using for the intensity colors for the point PS and PT, because these are known. So using this I can render the triangle, and if I can render one triangle, I can render all the triangles and get the intermediate image, right? Okay, so now if you look at the results, which are slightly now, so this is again source, this is destination, and you see that the eyes and nose sort of correspond. Right. So let me give you an example here. So this is tower in London, this is your Eiffel Tower. So you want to make a morphing between these two towers. Right. Okay. Now there is another sort of application you can use it through image morphing. So here in fact an interface is built where audio visual output is produced given the text of the speech. Okay. So there is a database made for different phonemes. So phonemes is the unit of or the lowest component of your speech. So there is a corresponding visual corpus or counterpart of the phoneme. So when you say P, then the lips are closed. When you say A, then the mouth is open. Right? So these form the visual counterparts of phonemes. Right? So we call it them visioms. Given that, in fact, you can do or perform a morpheme when you know the sequence of phonemes required to utter a word or a sentence. So you can process the speech getting these components in terms of phonemes, therefore the visioms, and then perform morphing of them. Right? So let me give you. So he's saying some how are you. Okay. Similarly here. Okay. So you basically you get the impression of visual speech. Right. So this project was done only here about 3-4 years back. So more details you can find out from the web page of our VG lab. Okay. Now let me actually give you another examples of this morphing, which actually were done as an assignment for image processing course. So here the idea, you see, this is one source, this is some sort of a target, this is an intermediate form, and this is the transitions you observe. Right? And here in fact number of keyframes are used. So it goes from 1 to 2 to 3 to 4 and so on, and you see it here. Right? So this is through morphing. So I don't know whether you have seen this Michael Jackson's song White and Black. Yeah. So that is actually using this. Okay, there's another interesting aspect to it which was done by these students. Actually, so some sort of an aging process. So this is an image of Yuvraj, and this is an old Yuvraj, somebody made it, and you see how this aging is taking place as a morphing process. Right? Anyway, so we stop here.